Flat Earth experiments. Determining the shape of the Earth using tools, observations, and measurements you make yourself, all in your own backyard. Part 7a. Speed of the Moon. This video will explore the second of our 5 moon observations, and will contain a fair bit that's the same as the video number 3 on speed of the Sun. The techniques are all different, so stay tuned. Recording the moon's speed can be done in multiple ways, so this video will only cover the speed relative to you, the observer. Future videos will cover the moon's speed relative to the Sun and relative to the background stars. Tools. This video will require that you have a video camera with a good zoom and not a smartphone camera, and a rock-steady tripod. You'll need to be able to download the video from your camera to your computer for analysis. We'll use elements from the last video on photographing the moon to record its size, as well as the math involved from video number 3 on the speed of the Sun. Here's a quick overview. We're going to record the speed of the moon at several times during the day. We'll do this at the highest point or peak of the moon's path in the sky and at either moonrise or before moonset. The flat Earth model says that the moon moves towards the viewer at moonrise and then away at moonset. Thus, the speed across the sky should be slower than at peak. The globe Earth model has the moon essentially at the same 240,000 mile distance, with moonrise and moonset due to the Earth's rotation. Thus, the apparent speed in the sky shouldn't change. Here is the plan of attack. First, we'll make 2 videos of the moon's motion across a small patch of sky. Each time you record a video, also take a still image of the moon for standardization purposes, similar to what we did in the last video on the size of the moon. Be sure you have your camera rock steady on a tripod as you record several minutes of video. You'll want to capture the moon moving several diameters across the frame. Then we'll analyze the 2 videos to determine the speed of the moon in diameters per hour. The next step is optional, standardizing the data. This will convert your units to a standard measurement, degrees per hour. This will be helpful if you want to compare your results with others or with yourself at a later date. Lastly, we'll take a look at the 2 models for the shape of the Earth and describe how our measurements might relate to the flat Earth model or the globe model. Step 1. Recording the moon. The first step will be to familiarize yourself with recording video of the moon with your camera and tripod. In the last video on size of the moon, there was a primer on taking good quality images of the moon. Be sure to consult the manual for your particular camera and get the details on exposure. The nighttime moon can be a difficult subject because it is a bright spotlight on a black background, so it is very easy to overexpose. Again, you'll use your dedicated notebook for this experiment. My favorite is a standard composition book. This slide shows a sample page that you can use to record your data. Pause the video here if you'd like the details. As in the last video, you'll want to record the official Moonrise Moonset times for your location using either your local newspaper or a website such as timeanddate.com/moon. A third choice is mooncalc.org. Any of these sources will help frame the times of your moon observations. How often and when to record the speed? Just as the video on the speed of the Sun, at a minimum you'll want to record the speed twice, at its peak and your choice of after moonrise or before moonset. Even better will be to bookend the speed at its peak with both moonrise and moonset speed. If you're ambitious and really want to act like a scientist, record the speed once an hour for the entire time the moon is in the sky. For best results, use this technique when you can see a full moon, or you could do it with a gibbous moon, or when you can see a half circle, called a quarter moon. You should not do it on days or nights when you can only see a crescent moon. Consult any calendar to see what the current phase of the moon is so you can plan accordingly. If you want to standardize your data, getting the moon speed in degrees per hour, you'll need to snap some full-frame moon photos and also photograph a reference photo. These procedures are detailed in video number 6, Size of the Moon. If you take careful notes, especially about what zoom level you use for both still images and for video, then you can perform both size of the moon and speed of the moon in one day or night. Here's a rough guide for how you want to frame the moon when shooting video. Zoom in or out so that the diameter of the moon is about 1/3 of the frame height. Record this zoom level, as you'll want to match this exact setting for both sessions. As you prepare to lock down your camera on your tripod, you'll observe the moon slowly drifting across the frame. You'll want to press record when the moon is up against one edge of the frame and stop recording when it nears the other side, or about 2 diameters travel distance. More footage is better than less, since we'll only be concerned with the middle section, discarding the very ends. Step 2. Computing the speed of the moon in moon diameters per hour. To compute the speed of the moon in both of your clips, we'll analyze the video footage you recorded. Before we measure the speed, we'll need to pick 2 times, a start time and an end time, for the endpoints of our speed measurement. These are called in and out points. Using either the play button or the scrubber bar, pick a good start time where the moon is fully in the frame, and then select a second time when the moon has moved at least 1 moon diameter away. Record your in and out points in your logbook. Now let's do a conversion to convert to seconds. This makes the math much easier rather than having to have everything in minutes and seconds. For each of your times, multiply the minutes by 60, then add the seconds, and this will result in both time codes in seconds only. Then subtract the first time in seconds from the second one to get an elapsed time in seconds. Record this in your notebook as well. We're now going to measure the moon's speed across the sky in moon diameters per hour. Use one of these 3 techniques depending on your digital tools. The first is using an actual paper sticky notes and a plastic ruler, which you can literally hold up to your monitor. The second requires the use of Photoshop, PowerPoint, or Keynote, or other slideshow app, which will let you layer 2 images with transparency. And the third is for video editors, using something like iMovie or Final Cut Pro or Movie Maker or some other software, which will permit you to have a video clip and also draw lines on top of it. Regardless of the method, the general method will be to first measure the moon's diameter and then measure the distance the moon travels. It is extremely important that you have your in and out times in front of you at all times. We'll be repeatedly jumping back and forth between the in and the out as we measure the moon's speed. Technique A. Stickies and a ruler. First, turn off the lights in your room and make your monitor or laptop screen as bright as it will go. Have your sticky notes, a pencil, and a pair of scissors handy. Move your scrubber bar to your pre-selected start time or end point. And then place a sticky note right over the moon, being sure the sticky adhesive part of the note is on one side of the moon. With a pencil and a very light touch, trace the circle that the moon makes. Cut it out and stick it on your screen. Then move the scrubber bar to your pre-selected end time and make sure nothing disturbs the video window, as you now have a paper circle representing the initial moon's position or in and the actual image of the moon at the final or out position. Now take your measurements with a wooden or plastic ruler. First, measure the moon's diameter and measure the distance the moon traveled using the same units, inches, centimeters, etc. To measure the distance, go from one part of the moon's arc at the start time, for example, the upper right, to the corresponding part at the end time, the upper right again. Here's a common mistake you want to look out for, measuring the pair of moons end to end, which is not how far the moon traveled. Technique B, slideshow app plus digital transparency. This technique will use a similar procedure as our equinox video, when we measured the angle of the rising or setting sun and the angle it made with the horizon. This will require that you be able to take screen snapshots of a rectangular window on your screen, such as using the snipping tool in Windows or Shift-Command-4 on a Mac. It will also require that you have software to layer the 2 images and apply transparency, such as Photoshop or a slideshow app such as PowerPoint or Keynote. First, open the video file of your moon's motion and move the scrubber bar to your chosen start time. Take a screen snapshot, being sure to capture the video frame. This is important. We do not want a moon and only an empty sky. We need that sky to be framed with the video player. Repeat with the video paused at the chosen end time, taking another snapshot. Now open both screen snapshots and take one image and turn the sky transparent using the Remove Background tool in PowerPoint or Instant Alpha in Keynote, or you could just use Photoshop. Carefully align the two images such that the outer video frames are perfectly aligned. Consider taking a third snapshot of this alignment. This is the image on which we'll take our measurements. As before, we'll find the diameter and the distance, but instead of using a plastic ruler, we'll use the line drawing tool in our software, allowing it to tell us how many pixels long it is. Be sure that when you measure the distance traveled, you pick a corresponding point on the two moons to accurately measure the travel distance in pixels. Record these values in your notebook. Technique C, markup by using an overlay on a video player. I'm not going to go through the exact details of this technique as I don't know what your favorite video editor is, but it should allow you to draw lines and circles on top of the video frame and continue to use the scrubber with those shapes and circles, or with those shapes on the screen. You should also have some technique for measuring the lengths of those lines in pixels. In your video editor, open your video file and move the scrubber so the timeline is at your pre-selected start time, or in. Then draw a hollow circle on top of the moon. Then move your scrubber to your pre-selected end time, or out, and either take a screen snapshot, or be very careful not to disturb either the hollow circle or the video frame. As described before, measure the diameter and the distance traveled in pixels. Record these values in your notebook. Computing diameters per hour. If you've done one of the previous three techniques, you should have the elapsed time in seconds, the diameter of the moon, using whatever units were convenient for you, inches, centimeters, or pixels, for example, and the distance the moon traveled, using these same units. This formula uses dist, diam, and time. Just multiply dist by 3600 and divide by the quantity of diam times time. This will result in moon diameters per hour. How does this formula work? It's using a very helpful technique called unit analysis or dimensional analysis. Here, pixels from numerator and denominator cancel out, as well as seconds. The only units left are diameter in the numerator and hour in the denominator, or diameters per hour. Step 3. Standardizing your data. Optional, only if you want to compare data with others. Here, we'll convert our speed in moon diameters per hour to a standard of degrees per hour. This will require that you've taken single photos of the moon in conjunction with your videos. Simply use the techniques given in video number 6 to measure the moon's diameter in arc minutes. Once you have the moon's diameter in arc minutes, you can convert the speed using this formula: diameters per hour times moon diameter in arc minutes divided by 60. You will now have the moon's angular speed across the sky in degrees per hour for future reference. The way the formula works is also by unit analysis. All the units we don't want cancel out and we're left with degrees per hour. Step 4. Flat Earth versus Globe Earth analysis. Again, in this series of videos, we're only considering two models, the Flat Earth model and the Globe Earth model. We'll start by looking at the behavior of the moon in both models so we can make sense of our data. On the Flat Earth model, the moon follows a circle above the equator or the tropics at about a 3,000-mile elevation. Again, let's note that the Gleason's Flat Earth map might not be perfect because all the distances might not be to scale. However, this does not change our analysis. The exact distance or location isn't important for analyzing speed because regardless of location on the map, except for the North Polar region, the moon moves towards or away from the viewer from Moonrise through its peak to Moonset. If the observer isn't near the North Pole, the moon will move towards or away from the viewer at the start and end of its journey across the sky. So why is moving towards or away important? If we have an object with a constant speed moving towards an observer, then the further away the object is, the less it appears to move, given by a smaller change in angle. This makes it appear to move slower than it does when it crosses closer to the observer. Let's translate this to the flat Earth, and again, the exact map isn't important. As with the last video, we're going to place an observer in Missouri near the date of the equinox so that the moon travels in a circle precisely above the equator. Let's simplify the map so that we're only looking at the region north of the equator where the moon is traveling in this example. If we focus on the constant speed of the moon traveling the full circumference of the equator in 24 hours, this means that roughly 12 hours of moon visibility, or 6 hours between the moon's peak and moonset, represented by the white circles here. Let's focus on the angles the moon makes in the sky for our observer between its peak and 1 hour later, and again for the hour before moonset. And notice the angle is smaller as the moon moves away before moonset. Making the map disappear makes the angles easier to see. Again, the moon is moving at a constant rate, but because it's further away close to moonset, it moves with a smaller angle. Thus, it appears to move slower. Let's focus on the triangle formed by Missouri and the two moons' locations at its peak and 1 hour later. Using the technique we showed in depth in our last video, we can calculate the distance to the moon, being that it's 3,000 miles in elevation. Knowing the entire circuit of the moon above the equator is completed in 24 hours, we also then know how far the moon moves in 1 hour. Again, we'll give the standard disclaimer that for purposes of calculation, we're using 3,000 miles. You're welcome to do your own calculations with your estimate for the flat Earth moon's height. This gives us three sides of a triangle, and using the law of cosines, we can calculate the angle shown in green. This will be the angle that an observer in Missouri will see the moon move in the sky in 1 hour after its peak. We're interested in the angle for our Missouri observer, so we can rearrange the law of cosines to solve for capital C. Plugging in lowercase a, b, and c, we find the angle to be 23.2 degrees. This means that when the moon is above the equator, an observer in Missouri will see the moon move at an angular speed of 23.2 degrees per hour near its peak. We can repeat the procedure using distances to the moon at the horizon, and we find the speed to be 11 degrees per hour at moonset. Again, objects actually moving at a constant rate, such as the moon, will appear to move slower when they're further away. This gives us a ratio of 2.1 times. The moon appears to move about twice as fast at its peak than at moonrise or moonset for the observer in Missouri. Here we've duplicated all these calculations for all the latitudes on the flat Earth. At the top is 90 degrees north latitude, or the North Pole, through the equator at the middle, through the ice wall at 90 degrees south latitude. For better precision, these calculations are based on paired observations of the moon's position 10 minutes apart. This reflects what we've done in our experiment, recording the moon's position in the sky over a span of roughly 10 minutes or less. To help you find a ratio estimate for anywhere on Earth, you can use this map. It shows the ratio of how much faster the moon appears to move when at its peak compared to near the horizon. Read between the lines to estimate for your location. Now let's discuss the globe Earth model. The globe Earth model has the moon about 240,000 miles away, and the Earth's rotation causes the moon to appear to rise and set. The heliocentric model has the moon very far away from the Earth, and it is rarely drawn to scale. What you see here is the correct scale in the globe Earth model. Here's a demonstration of what an observer on the equator might see when the moon is at its peak and when the moon is rising. This diagram is not to scale, just to illustrate the change in angle as the Earth turns, as we look straight down at the North Pole. As the Earth turns over 16 minutes, it moves 4 degrees. Thus, both observers see the moon 4 degrees away from where it was at the start. This means that in the globe Earth model, the apparent speed of the moon won't change from horizon to peak because the moon is so far away. To review the two models and how they relate to the speed of the moon in the sky, in the flat Earth model, Moonrise and Moonset are caused by the moon moving towards or away from the viewer, using the law of perspective and the vanishing point. Although the moon is actually moving at a constant rate, when it is further away at Moonrise and Moonset, it will appear to move much slower than at its peak. In the globe Earth model, Moonrise and Moonset are caused by the rotation of the Earth, in comparison to a very distant moon. Thus, the distance shouldn't change. This relatively constant distance means the moon should move at a constant rate in the sky in one day or night. So, how does your data about the moon's speed relate? If it appears to move significantly faster in the sky at its peak than at Moonrise or Moonset, this supports the flat Earth model. If the speed stays more or less the same, this supports the globe Earth model. Again, note that this doesn't prove anything. The data you gathered simply might support one model over another. Please consider sharing your results at the message boards created by Cara Diane. This is not a place to debate, simply a place to share your data with other like-minded individuals. To be even more certain, more data gathering is needed from a variety of sources, as we'll discuss in the rest of the series. We're going to have two supplemental videos for speed of the moon, 7b, speed relative to the sun, and 7c, speed relative to the stars. After those will be number 8, phases of the moon. Again, for best quality photography, you'll need a good zoom camera. When commenting on this or any other video, please keep an open mind and remember to be kind to each other. Practice what Stephen Covey recommends. Seek first to understand, then to be understood. Thank you.